Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over subsequent ionization energies. So in a previous video I talked about ionization energy as being the energy needed to remove an electron from a neutral atom. But what if we remove more than one electron from an atom? We can always remove more than one. So we can always have those what are called subsequent ionization energies, where we remove electron after another, and we look at the energy it takes to remove those subsequent electrons. So let's go ahead and look at a couple of examples. So here I have magnesium, and here's the Bohr model for magnesium. You'll see that magnesium has two valence electrons in its third energy shell, and then it's got these core electrons in the second and first shell, respectively. And then I have aluminum down here. We'll get to aluminum in a moment. Now, so in this table here, this table I put down, I have the energy that it takes to remove the first electron, the second, and the third electron. And so the energy it takes to remove that first electron is one of these electrons will be removed. So we're going to remove the valence electrons first because those are the easiest. Why are they the easiest? It's because they are farthest from the nucleus, and so they're not feeling as large of a pull as the inner electrons, the core electrons are. So if we're going to remove a one electron, the first one's going to be one of these two electrons. So we remove one of those electrons, so we'll remove one. Okay, so this one removed. Let's call this E or IE1 for ionization 1, the first ionization energy. So we remove that electron. Well, how much energy does it take? Well, it takes 738 kilojoules per mole of energy to remove that electron. Okay, so that's the first electron. So then what do we do? How much energy does it take to remove the second electron? So when we remove the second electron, that one goes away, and we'll call that the ionization energy 2. So IE2, the second ionization energy. And so you'll see on this table here that the energy to remove that second electron was a little bit more, 1450 kilojoules. Well, why did it take more energy to remove the second electron than the first? I mean, aren't they both valence electrons? They're both in the same shell. So why is it that they have different ionization energies? Well, the reason is because when you remove that one electron, we're removing repulsive forces. So remember, these two electrons, even though they're in the same energy level, they are acting on each other. There are repulsive forces. They're both negative. So Coulomb's law still comes into effect here. And so that is going to cause some shielding. Remember, the excuse me, the repulsive forces of the electrons is what is shielding the electrons from the attractive force of the nucleus. So the fact that you remove this electron from the atom reduces some of that repulsive force, and therefore reduces some of that shielding, and therefore this electron is able to feel more of the effective nuclear force, and so therefore it's going to take a little bit more energy to remove that second electron. So here we have about double the amount of the energy it took for the first one. So then we got both of these electrons removed. Now we're going into the core electrons. We're going to the next energy level, the next lower energy level, and we remove one of those electrons. So that would be the third electron. And so we'll remove this one. So that electron gets removed, and so the energy it takes to remove that will be the ionization energy 3, IE3, the third ionization energy. And what we notice is it takes a huge amount of energy relative to these two to remove that third electron for magnesium. Well, why is that? Here, the reason is not only are we removing the electrons and removing that repulsive force, but the next level of electrons are much closer to the nucleus. And so that distance to the nucleus makes the attractive force a lot stronger. And so it's going to take a lot more energy to remove one of these electrons than it is to remove any of these. And so the next time this third electron takes a huge amount. So it's about, what is it, three times, 3 or 4 times the difference from here to here, whereas between here and here is like double. So this amount is a huge amount relative to these two. And then if I continue to take out electrons, since these electrons in this shell are in the same energy level, they're about the same distance from the nucleus. So then now the difference is going to be less repulsive force. So I would expect that removing the fourth electron here would be higher, but not as big of a jump as I see here. Okay, I hope that makes sense. Let's go ahead and do aluminum for another example. So aluminum here has 3 valence electrons. So these 3 valence electrons are removed first before we get into the second energy level. So what we notice again is when we take away that first electron, right? So we put in our first ionization energy. That is only about 578 kilojoules per mole. So relatively small amount. Then we take away the second electron. That'll be the second ionization energy. And that amount of energy is a little bit more. Again, the reason it's more is because when you remove the first electron, you're removing some of that repulsive force and therefore shielding the not as much shielding. And so the second electron that I remove is feeling a greater force from the nucleus, and so it takes more energy to remove. And then I remove the third electron, so that would be my third ionization energy. And you'll see here that it jumps up a little bit, about 1,000. So here I'm going from 578 to 18. So that's a jump about somewhere between 2 and 3 times the amount. Here, going from the second to the third energy, ionization energy, um, it's not even, it's about 1,000. So not even double the amount of energy it took to remove this one. So these are relatively small increments. So they're not requiring as much energy. Um, so this would be your ionization energy number 3. And so now we've removed the 3 valence electrons. And then the next electron, the fourth one of these in here, that's going to require a lot more energy. So 11,600 kilojoules per mole. So compared to this one, there's like almost 5 times the difference between removing your first core electron versus your last valence electron. So when you're removing valence electrons, the amount of energy you're removing in subsequent removing of the electrons, the energy doesn't go up very much compared to when you remove your first core electron. So it's a very huge difference between your last valence electron and your first core electron. So same thing here. So first 2 were valence electrons. Your first core electron is a huge jump. So given this information, given that what we know now, we can identify how many valence electrons an atom has if we're given the subsequent ionization energies of that particular atom. So here's an example that I kind of made up. You don't even need to know the numbers. So here's our unknown, and here's my kilojoules per mole, and the first, second, third, fourth ionization energy. So I can identify from this graph how many valence electrons that this atom has. Can you? So pause the video for a moment, see if you can figure out how many valence electrons does this element or this atom have. Okay, so you're back. Have you figured it out? So here, notice the trend here. So you have this first ionization energy is a relative small jump in energy here, right? So this is the amount of energy. The second ionization energy to remove that second electron is very big compared to this. So there's a huge jump here, but then for the third and fourth, very minor jumps in energy. So these three here are very close to each other, not a large jump, but between this, the first and the second, huge jump. So what does that tell you? That tells you that this first electron was a valence electron, and the next one had to be your first core electron. So that means that whatever this element is, it has only one valence electron, which means it has to be a group 1 element, since we know that the group 1 elements all have one valence electron. So we at least know that this element should be in group 1. I hope this was helpful. I hope you learned a lot. If this was fascinating, great. Hit that like button, share my videos, subscribe to my channel, hit that notification bell so you can be notified of videos that I put out. Put a comment in the comment section. Let me know what you think. Ask me questions. Thanks for joining me. Have a great day.